Hi guys, I'm just going to whiz through some stuff that you should have learnt in GCSE, and I'll make a summary notes on this slide, trying to take some screenshots of what I'm going to do. So we don't need this access, these axes, because we'll use actual shots out of Desmos. There are 4 alterations we're going to make to these. We're going to analyse them individually very quickly, and then just quickly talk about what these transformations are as well. So we'll do them one at a time, A, B, C, D. And I'll try and give you a little insight into the oddness of why the values are manipulated in that way. And the way to think about it, if you want to get the understanding, is consider what's happening to the domain and range when you do these operations on them. So whatever's going inside the function is going to be what you think is happening to the domain. Everything being done to the function is the range. Okay, so that's what we're going to be focusing on a little bit. So enough with this graph, we'll go and have a look at Desmos. So we've got a basic cubic graph, which one of my favourite example ones is this one. And the function, the solid line function, which I'm going to change to green. Actually, let's make it blue. So the blue function that you can see on top of the red dotted line there, that is the result of what happens when we multiply the function by a there and the x value by b, and when we add values to them. So you should be familiar that if I change a, the value, the coefficient of the function, it's going to affect the range. All the y values change. And the way they change is, if I change that to 3, all points get 3 times further away from the axis. So let's just zoom out a little bit and move that up for now. So if we do a function, the dotted line, and multiply it by 3, all points get 3 times as far away from the axis. It's a scale in the vertical direction by a factor of 3. That's the note. So A becomes scale, the y direction, by a factor of 3. And this y direction thing, if you're doing it properly, we should say parallel to the y-axis, or perpendicular to the x, either the same. Okay. Second one, let's move a back down to 1. Notice the function is a scale factor of 1. Let's change the d value, the value on the outside. Move this down again. When I move this up to 2, it's moved in the positive value by 2. Every point on the graph has moved 2 vertically. So again, so D is translate. In y direction. Or again parallel to the y-axis. So that shouldn't be 3, that should be A, by a distance of, sorry, I've got C and D wrong way around on my notes, so let's just move them. Miss the R and the Y out. And I think I better put a note in there, an extra line in that one. Like that. There we go. Give me some. So anything done to the function on the outside affects the range. Okay, the range is affected by it. Now the odd one that people have is what happens in the other two, so by distance, and I'm going to stick to the notes in here, C, and I'll change this so that C and D the right way around. So D and C, and make that one 0, and that one 2. So there, that's the problem we've just done. Let's put it back. Next one we're going to consider is the value on the D, the bit that affects the X values, therefore it changes the domain. If I increase D by 1, 2, 3, 4, 5, let's go for 4. Notice the graph has moved backwards. One way to think about it is what this graph is saying is at the point -4, add 4 to your X value and tell me what F was doing. So it's actually saying look forward 4 places and tell me what the graph was doing, which means the graph translates the opposite direction. Okay, so the D one at the bottom is a translate in the x-axis or direction by a distance of -D. Notice it changed around because it's saying look this much further. And the same thing happens for the G function, the function when you multiply on the domain. So there's my domain multiplier. If I double my, I've tripled it there. What that's saying is for the point at 1, which is here, triple the distance from the origin and tell me what the function is doing. So to get this point, triple the distance and see what the function is doing, copy it to this place. Notice the gradient isn't copied but the position is. And the net effect of that is you actually do the same thing. So the factor that you've now done, you've done an x direction stretch which takes everything 1/3 of the distance. Hopefully none of that is a surprise to you. So a scale x direction or parallel to the x-axis, parallel to x by a factor of 1/b. That should be your summary. Now I'm just going to put some graphs in and complete the notes for the moment. So pause. Okay, I've got my notes tabbed in now, so we can quickly add to these the transformations that happen. So what actually happens here is everything multiplies by the factor A in the y direction, so it affects what the range of the output would be. This one moves, this one doesn't actually show any positive directions, so multiply by A, and you could actually also multiply by A that way, depending on which direction of the side it is. Everything on the translations, everything moves in the same direction by the factor, the amount C. When we come into multiplying, what we actually have here is the x direction is multiplied by 1/b, so it would halve in this case. So this b is 2 and this is halved, and this one, it moves everything in a definite direction of -d value. Okay, so that's the summary of those graphs. Everything, we've got a scale, a translate, a scale in the x direction. So this is a translate C0. We've got a translate, so 0C, isn't it? translate minus d0. It goes the other way to the sign on the x values. Okay, so that's what happens when we come into doing normal functions. The modulus has some really weird effects, and I'm going to use that same sine function. I'm going to take these domain limits off them. We don't need them. I don't think we actually needed them then either. But we're now going to note what happens with the modulus function. So what happens when we do g of x is the modulus of f of x. Now before we start looking at any, just think, this says that any y value output that is negative becomes positive. So that actually tells you immediately that unless you're doing anything outside this function, the range for this of gx is greater than or equal to 0. As soon as you see that, you know that's what's happening. Okay. So let's have a look at what happens to our cubic curve when we do this modulus function. So we've got the original cubic, and for every point where the graph is above the line, it all matches up. Actually, I said I'd get rid of those two. Get off. So where the dotted red line is above the x-axis, so we've got a positive y value, it's the same function. But for every point where it's negative, it inverts itself and draws us a copy that's been reflected. But in itself, it's not a true reflection. It's only a partial reflection. It's a reflection of only the negative values. So I just want to take that. If you want to know what I did, I used Window Shift S, and it allows me to select my window. That's slightly different for the operating system, but you are allowed to do it in your normal windows as well. So if you do the modulus, what the modulus on the outside of the function says, take all values that are negative in the range and flip them to their positive. So this region, copy fx, and for this region we copy the negative of it, so it flips over, so it only actually operates in this bottom area. That one, fairly straightforward. What might be a surprise to you is what happens if we do a gx and we take the modulus of the internal function. Now I'm going to use a different function for this, and you might see why. So doing a slightly different function, let's see what's happening. Now we've got our, actually I'll go back and we'll look first at the other one and then come back through to this. No, we can't. Well, yeah, we can. Let's just clear out all this other stuff. So x to the power of 3 minus 3x to the power of 2. Now, same graph we've had before. I'll just remove that function. So there's my graph, and we've got to think, if I put the modulus on the x values, it says that when I go to minus 2, look at what x is doing when it's plus 2. Copy the point. So we get a point over here. And it does that all the way through. So all this stuff on the negative x side is ignored. We never try -1, we never try -2, because they all turn positive. So what actually happens for gx, so remember absolute is the modulus function, is you actually get a symmetry of the positive side. It actually makes a complete reflection in the line x equals 0. Okay, so I'll just take that back to our notes. So this actually winds up reflecting in the y-axis. All our points. And that actually means that if we've got something that's undefined for some values negative, like the square root of x, let's just do the square root of x. What we can get is, we get the original function, which is just defined above, but now when I do the modulus of that, I also get all reflected values. So if the domain of fx is x greater than or equal to 0, the domain of the function that's modulus of it is actually x becomes a member of all real numbers. Okay, so it reflects the y value, so fx is actually then can be defined as a piecewise, can be defined as when x is greater than or equal to 0, it is fx. When x is less than or equal to 0, or less than 0, only one of these should ever operate at the same time, it is the value of negative x. So that changes the sign. Okay, so there's the modulus function. The modulus function in the y direction cuts the range in half and gets rid of anything that's negative output by reflecting it above. And the modulus on the x before it goes into the value. So before we do the function, if we do the modulus first, it means we wind up with a reflection on the for the negative. So the line of reflection would be when x equals 0. So don't forget that's x equals 0, the line. Okay, that should be your notes for that. Go and have a look at I think that's the rest of the chapter. Now we have one more section to do, section G, which is about solving modulus functions. So you should be able to now do exercise 2E and 2F in your textbook. Let's just help you find the pages as well. So 2E is on page 30. Oh, sorry, I'm missing one as well. You should also be able to do. Oh no, there was 2E, 2F. 2E is on 30. And going on, and 2F begins on page 34. Hey guys, there you go. So we have one more section to do, which is solving problems with areas and modulus functions.